Truth functions. What are truth functions? Truth functions are generalizations of the familiar connectives negation, conjunction, disjunction, implication, equivalence. By focusing on the general concept of a truth function rather than each individual connective separately, we can understand the nature of connectives better. One of the main reasons to study truth functions is that computers are ultimately based on truth functions that are welded into microprocessors inside the computer. Also, truth functions have interesting mathematical properties, and truth functions turn out to have a close connection to propositional formulas. A truth function, also called a connective, is any function f from the set 0, 1 to the power n to the set 0, 1 for some n. A truth function of n variables is called n-ary. A two-ary truth function is called binary. Truth functions can be identified with truth tables. Because we can simply list all the values of a truth function, note that there is a big difference to functions on infinite domains such as n and r, natural numbers and the reals. A truth function has only finitely many arguments, and we can simply make a list of all of them together with the values that the truth function gets on those arguments. Such tables we call truth tables. We have already defined the connectives negation, conjunction, disjunction, implication, and equivalence. We identify these with the corresponding truth functions. So a connective is a symbol with certain meaning, but we can also think of it, indeed identify it with, a truth function. Negation is the truth function which maps 0 to 1 and 1 to 0. Conjunction is a binary truth function which maps the pair 1, 1 to 1, the pair 0, 1 to 0, the pair 1, 0 to 0, and the pair 0, 0 to 0. Similarly, the other connectives. Here are some examples of truth functions. In the first one, the value of the function is constant 1. This may not be the most interesting truth function, but it is a truth function all the same. In the second truth function, the value of the function is 1 if the arguments x and y have a different value. The third truth function is again a constant function, this time constant 0. Again, we leave aside the question how interesting this function is, because from a mathematical point of view, all functions are equal. Our fourth truth function may look familiar. This is the truth table of the connective equivalence. Our familiar connectives pop up as truth functions, but there are also others. Here is a table of all binary truth functions. The table starts on the left, after the column for the arguments x and y, with the rather boring constant 0 truth function. Then comes a function that is 1 only if both x and y are 0. After an odd one, we can see the truth table of the negation of x. then again an odd one, and then the negation of y. We skip over two functions and come to the truth table of conjunction. And immediately after that, the truth table of equivalence. Then we have the identity function y, after which comes the important truth table of implication. Then we have the identity function x. After the truth table of y arrows x, we find the truth table of disjunction. And finally, the constant function 1. The important connectives, negation, conjunction, disjunction, implication, and equivalence, seem to appear somewhat nondescriptly in the table of all binary truth functions. Their important role in our everyday language does not jump on our face. In fact, many of the binary truth functions could have emerged in our language and overshadowed connectives such as disjunction and implication. Why this has not happened? When we proceed, we may perhaps get a clue what is so special about these connectives: negation, conjunction, disjunction, implication, and equivalence. If we made a similar table of all ternary, triary truth functions, there would be much more cases simply because there are much more ternary functions than binary ones. Here is an example of a ternary truth function. This truth function does not have any particular intuitive interpretation, but in a moment we will learn how to associate a propositional formula to each truth function. The propositional formula can then give a kind of intuitive picture of the truth function. Also this one. Here is an important new connective called Sheffer stroke. It is also known as NAND, coming from the words not and, because as one can easily see, this truth table is like the converse or negation of and. When we learn about definability in a moment, we can see that Sheffer stroke has remarkable properties. Its importance is not in that people might use it in everyday language as quote not and unquote, but rather in its power to define every other connective, as we shall now see. Definability is an important concept in logic and occurs in many disguises. A truth function f is said to be definable in terms of truth functions g1 to gm if f can be obtained by composition from g1 to gm. What this means in practice is the following. Disjunction can be defined in terms of negation and conjunction. Technically speaking, the connective disjunction can be obtained by composition from the connective negation and conjunction. Composition means roughly speaking the same as successive application. Like in the above definition of A or B, we first apply negation to A and to B, then conjunction to the result, and then finally once again negation. Similarly, Sheffer stroke A stroke B can be defined in terms of negation and conjunction. On the other hand, negation and conjunction can be defined in terms of the Sheffer stroke. So we see the interesting property of Sheffer stroke, that negation and conjunction can be defined in terms of it. Since disjunction can be defined in terms of negation and conjunction, we may conclude that disjunction too can be defined in terms of the Sheffer stroke. This interesting property of the Sheffer stroke is called universality. A set T of truth functions is universal if every truth function can be defined in terms of functions in T. Respectively, a function f is universal if the set singleton f is. It turns out, we will give an argument to this effect in a moment, that every truth function can be defined in terms of the Sheffer stroke. That is, the Sheffer stroke is a universal connective. Microprocessors are built from gates that are essentially connectives. It suffices to manufacture Sheffer stroke, or so-called NAND gates, as all others can be built from them. The sets consisting of negation and conjunction, and also the set consisting of negation and disjunction, and the set consisting of negation and implication are also all universal. This needs, of course, to be proved. So let us move on.